I will do some kind of a gentle introduction to computational optimal transport, trying to insist a bit on the limitation and what we have been trying to do recently to a bit alleviate these difficulties in high dimension. And this is a joint work with a lot of people, but I would like to speak a bit about Aude. So it's mostly the PhD works of Aude, and also a collaboration with Marco, which introduced a lot of this idea of regularization, which I will speak about. So, and a little bit of advertisement for this book. So if you want to know more about optimal transport, the computational aspects, so everything that I will discuss today, including slides, code, lecture notes, just go to this web page where there's a book we have written recently with Marco. Before I start, a bit of motivation. So why should we care about manipulating, comparing probability distribution, point cloud, densities in data science? I think it's because many problems could be framed this way. For instance, if you think about more like low-dimensional problem in imaging, where you want to understand, manipulate the color or maybe other feature in images, you gather them in some kind of a bag of feature representation, like the color palettes. In neuroscience, if you think about the activity on the brain, you might want to represent this activity as distribution of mass on the cortex and probably monitor it. In shape analysis, in medical imaging, computational anatomy, the big problem is registration, trying to compare together shapes. And here, once again, it makes sense to view the shape as distribution of mass you'd like to register together. And it's a pretty common practice. So this is more for like low-dimensional settings. But of course, in machine learning, you also witness these problems of fitting, of parameter estimation, could be for supervised learning. And there is a huge trend nowadays in natural language processing to represent words as points in a high-dimensional space. So here, comparing text, doing regression or prediction would requires you to understand the geometry of point clouds, which represent the text. And this is even more ambitious. This is about understanding the geometry of images. So if you think about a huge collection of images and wants to do some unsupervised learning, this would be equivalent to understanding the geometry of a huge collection of images in some kind of abstract space. We don't really know what is the space of images, but there is a lot of revolution going on recently with all these GANs, so generative adversarial networks, where people are using deep nets to model this geometry of a large collection of images. So a typical setup in all these problems, supervised or unsupervised, is about density fitting or parameter estimation. You are given as an input a huge collection of empirical observation points in a high-dimensional space, and you want to capture them using some parametric models. So this would be some kind of a density parameterized by some theta. So it could be a simple model, but of course in high dimension, this would be like deep net model to parameterize the density. And you want somehow to make this parametric density be as close as possible from your observation. So of course you could frame this as some kind of an optimization problem where you want to minimize some discrepancy between your model, alpha theta, and your empirical data. And the question I will try to address in this talk is what should be the D function you want to use. And the key observation is that the D function should take into account the geometry of the underlying space. In all these setups, the points are not just abstract objects. They live in some space. Could be the space of colors, could be the surface of the brain, could be a kind of geodesic distance. Here for natural language processing could be the space of embedding of the word in a Euclidean space. And here, I've already said this, but it's very complicated. But using deep nets, you can try to model the space of images. So the key idea of optimal transport somehow is that it's going to be a machinery, an automatic method based on optimization that takes as an input some distance between points and give you a distance between more complicated objects, point cloud or measures. And this is what I want to explain, and explain the limitation challenges, the limitations, the computational challenges, and also the statistical problem that you have in high dimension in terms of discretization, because this is very challenging in high dimension. So I will start by introducing this idea of Kantorovitch, which is quite old, but it's a very fundamental idea which really is the start of modern optimal transport, because optimal transport is very old. It was introduced by Monge more than 2 centuries ago, but the key revolution is the one of Kantorovitch, who gave the modern formulation, and then explain how to go further. So I will explain everything in a discrete setup, okay? But everything I say basically is the same with arbitrary density. You just replace sum by integrals, and it's exactly the same. But the question is, how do you compare weighted point clouds, so discrete distribution of data, which are just points equipped with some weight A and B, which should be positive and basically sum to 1 because it's probability distribution. And the key idea of Kantorovitch is to describe the displacement of mass between the points using what he calls transport plan or coupling. So what is this object? It's just an array of positive numbers, okay? And each time in this array you have a non-zero element. For instance, here there is a non-zero element in the first rows. It means you would transfer some mass from this point to this point. So here it's like a deterministic movement of mass because there is a single non-zero element. But really the key insight of Kantorovitch is that sometimes you need to be able to split the mass. So if you look at the second rows, you see that this map gets split into two parts, which will be mapped on the first point and on the second point. And he got the Nobel Prize in economy for this simple idea that if you don't split the mass, there is no solution. If you want to map a single point to two smaller points, of course, you will need to split the mass. Okay, and this is what makes optimal transport possible in theory and in practice. Why? Because what do you need this array to satisfy? You need to satisfy the conservation of mass. You need that the sum along the rows should match to A, and also the sum along the column should match to B. In matrix notation, P times 1 should be A, and P transpose times 1 should be B. So the set of optimal transport plans is just a gigantic polytope in high dimension. So it's a convex polytope. So you describe the set of possible transfer of mass using a convex language, the language of convex programming. So what is it going to be, the optimal transport? It's just going to be, among all these possible couplings, you pick the one that minimizes a cost, where you say that the price you have to pay to transfer some mass from xi to xj is proportional to some cost. Could be any cost, but the usual practice is to say that this cost would be some power p of the distance. Okay, so you pay a price which is proportional to the distance to the power p. And this is what gave him the Nobel Prize in economy, because it's a key way to use it for economic application, where you want to optimize some way to couple between production and consumption. Okay? But of course, here I would more try to insist on the impact of this idea on data science. Okay? And I also try to say that although he didn't get the Nobel Prize for this, George Danzig should have got the Nobel Prize, because he made the contribution of the modeling side. But of course, if there is no algorithm, it's useless. And in the same time, there was this introduction of the simplex algorithm by George Danzig, which is a very efficient way to solve this problem for medium-sized situation. And you can show that some instantiation of the simplex algorithm have complexity n cubed, where n is the number of points. It's either very cheap if your n is quite small, but of course in data science, where n is of the order of the billion or the millions, it's just going to be too expensive. Okay, so one key aspect is how do you scale in terms of n instead of having fast algorithm, and I will also discuss after about the discretization problem of moving from continuous to discrete. All right? So please stop me if anything is unclear. You can try to be slower if you want. Okay, so as I say, everything you can formulate using arbitrary densities, you basically just replace discrete couplings by continuous coupling measure, and you replace sum by integrals. And the very important point I would like to insist is, okay, it's cool because it gives you access to this transfer of mass, which is nice. You can use this as kind of a morphing between point cloud. But what is even more important is that it gives you access to the value of this optimization problem. Because if you take the power 1 over p to the value, it defines what is often called the Wasserstein distance, the p-Wasserstein distance. Although Wasserstein has very little to do with it, it should rather be called the Kantorovitch distance, but usually people call it the Wasserstein distance. So it's a distance, which first is not so trivial. So it means it satisfies the triangular inequality. It's 0 if and only if the 2-point clouds are equal. So it's cool. But you might argue, okay, I know tons of other distance on densities. Why should I pick the Wasserstein distance? And the key aspect is that the topology induced by the Wasserstein distance, the geometry it's induced on density, on probability, is really the geometrical one. So in terms of probability, it means it's geometry of the convergence in law. Okay, so I guess most of you already know what it is, but convergence in law is just convergence of expectation. It means integral on arbitrary continuous function should converge. And a simple example why it's important and why simpler notion of distance would not make the work for data science is a simple example of convergence in law is just a Dirac here at some location x, and the location converges to some limit point x. And this is a typical example of convergence in law. If you pick probably the simplest distance between probability, which is just the total variation or the L1 norm, what is the total variation between two Diracs? If the two Diracs doesn't coincide, it's just going to be 2. So it means in terms of convergence in law, the total variation doesn't converge. The total variation induce a strong topology on the set of measures, whereas the Wasserstein distance induced the weak topology, which is the correct topology because you want really to be able to monitor convergence of the support, convergence of points. So this is a key aspect, and I think you should care, if you care about registration or geometry, to use something that is smooth with respect to the convergence in law, which is a typical example is the Wasserstein distance. Because what is the Wasserstein distance between two Diracs? Well, there is a single way to map a Dirac to a Dirac, and the Wasserstein distance is just going to be the ground distance itself. And in some sense, it's the canonical way and the only way to lift a distance between points into a distance to a group of points that satisfies this conservation. So it's really like almost like the canonical way to define a geometrical distance. All right. Okay, but so what is the problem? The problem is it's quite expensive to compute. It's a linear program, but linear programming, in some sense, it's very flat. It's very hard to solve. And also, it's quite unstable. And I will give some example because of the polyhedral nature of the problem. So here, what we will do is to somehow simplify the problem, approximate it, because in many situations, maybe you don't care about having high precision solution. And in high dimension, I will actually argue that you don't want high precision solution because of numerical instability and problems in high dimension that I will explain. So the idea actually goes back to Schrödinger as a model for gas, the lazy gas model, is to replace the optimal matching, the optimal transport, by introducing a penalty, which is just epsilon times the entropy. And just a little bit of explanation on this. So when you speak about entropy, actually you always have to speak about the entropy with respect to some reference measure. The entropy in itself doesn't exist. You need to speak about the entropy with respect to some reference. But fortunately, with optimal transport, we have the natural reference measure. It's just the product of the two input distributions. Okay? And it's a bit technical, but it's very important for all the theories that I will explain to be working well, including extending this to continuous distribution. So you penalize epsilon times the relative entropy towards basically the input distribution. As epsilon goes to 0, you recover the optimal transport. So a typical example would be if you take two sets of points with the same number of points. Actually, it's a famous theorem. It's called the Birkhoff-Feynman theorem, that optimal transport is equal to the optimal matching of Monge. So the solution is just a bijection. And as you increase epsilon, what I'm showing you is little segments. Each time the coupling is larger than 10 to the minus 2. Okay? And you see that there are more and more segments appearing, meaning that as the temperature increases, you get some diffusion, and you get more and more points connected together. And it's really what will make the algorithm simpler, more efficient, and also much more stable in high dimension. Because if you move a little bit your input, a little bit of noise, you will see all these little segments moving all around. And it's typically the kind of instability that you get with linear programming. And of course, as you increase epsilon, it's like kind of a denoising. It will make everything much more stable. And this denoising effect is clearly visible if you think now of continuous densities, two very nice 1D densities that you couple. And once again, there is a very famous theorem due to Jan Brognier in 91, which created, I would say, the second revolution of optimal transport with the field medals of Villani and Figali, is that the solution of optimal transport is also somehow a deterministic map, because the coupling you get is very sparse and is located along a 1D function here. It's a bit hard to see, but this is Brognier's theorem. So as you increase epsilon, the solution of now the Schrödinger problem would be somehow more and more blurry. So you would add more and more diffusion, and in the limits, you get something very blurry, where you transport mass from everyone to everyone. So really, epsilon is like a temperature which interpolates between two very different things. And later on, I will insist on this and explain a little bit what are the two limits on the left and on the right. So on the left is optimal transport, and on the right, you see there is also a very natural large temperature limit. So this idea dates back to Schrödinger, but of course, Schrödinger was not thinking about optimal transport at all. So the idea is now, can we use this idea in practice? The first very, very important point is that this minimization is associated to a very simple and efficient algorithm. And what it is, this algorithm is often called Sinkhorn algorithm, because Sinkhorn is the first one in '64 that proved its convergence. But it's also a very old algorithm. Actually, it's much older than Kantorovitch. So it has many names. It has a Wikipedia page, so I guess it means it's quite a famous and an algorithm you should care about. For me, it's like a numerical algebra gem. It's really a beautiful algorithm. What it is? Well, it's just start by a remark, is that this is like a maximum entropy method, maximum entropy problems. So the solution, you can always write it using a Gibbs distribution. What does it mean? It's that being a solution to this problem is equivalent to the fact that your coupling, you should be able to factor it using a Gibbs kernel. So what is the Gibbs kernel? It's just exponential to minus the cost to epsilon. So if you think about the Euclidean case with p equal 2, which is the most celebrated case, then this would be a Gaussian kernel. So you should be able to factor your coupling using a Gaussian convolution, a Gaussian blurring. And of course, you need to adjust two sets of weights, one on the left on the rows and one on the right on the column. So instead of having to look for a big matrix, you need to look for two vectors, which is a bit simpler, I would say. And what do you need to solve? Of course, you need to solve for the conservation of mass. So optimal transports through this prism of entropy just become solving two nonlinear equations in U and V. What are these equations? If you write down what it means to conserve the mass, the first one is just that U multiply entry-wise by the vector k times V is equal to A. And the conservation of mass on the other direction, you just switch the role of U and V. Okay? So now you need to solve two nonlinear equations. Of course, you don't know how to solve it because it's as complicated as the first problem. But you see now the two equations have a very nice structure. So the idea of Sinkhorn is just solve each equation iteratively. So you start by this equation, and you notice that if you give me the value of V, then it's trivial to know the value of U just by dividing entry-wise A by K times V. So the first step is just do this update. This will solve the first equation, and then you solve the second equation the same way. And what you do is like a chicken and egg problem, you just iterate between the two. So it's like a fixed point algorithm. In practice, if you fixed point algorithm, there's no reason for it to converge. But the beauty is that this converges. And actually, you can show that it's contractant for a very famous metric, which is known as the Hilbert metric. So Hilbert metric is a metric on any cone, but in particular, it's a metric on the cone of positive value. So it's exactly an extension of the Perron-Frobenius theorem, because this is like a Perron-Frobenius iteration in some sense, except there is a 1 over. But if you think about it, it's really connected to Perron-Frobenius theory. Actually, this algorithm is also known as the nonlinear Perron-Frobenius theorem. It's a beautiful result. It converges fast, linearly. And also, it's something that you can implement very easily, because the only problem is matrix vector multiplication. So each iteration will cost you n squared, sometimes even less, because if it's a Gaussian kernel, you can more or less apply Gaussian convolution in linear time. And it's very connected to Joel's idea where you could use faster linear solver, faster method in some cases. Introduce sketching also. There's some paper by Francis Bach recently that use sketching for this algorithm. So there's many ways you can meet n squared or even smaller. And the other very important point is that this is trivial to parallelize. If you have to compute millions of optimal transport at the same time, what you would do is you will just store the U vector in a big matrix, and you would parallelize using matrix-matrix multiplication. So the key insight of Marco Couturier was to say this is an algorithm you want to implement on GPU. Because if you switch from CPU to GPU, then this is really a game changer. You gain order of magnitude. So I think really the setup that is the one you should use for this algorithm is basically GPU, which is now really it's very simple to use using whatever library like PyTorch or TensorFlow. So it's really something that goes extremely well with the advance in deep learning, I would say. All right, so what can we do with this Sinkhorn divergence? And why is it interesting, I would say, in practice? The first thing is rather a bad news, is that because of the entropy, it's not anymore a distance-like function, because when you compare alpha to itself, you have to pay the price because of the entropy, so it's not going to be zero, it's going to be strictly positive. So it means that if you use directly the Sinkhorn algorithm to do the fitting of two distributions, it would be a disaster. And really what you observe is if you increase epsilon, you would see some kind of bias, some kind of entropic bias. Here it's a simple example where you have the blue point cloud, and you want to find the distribution alpha, which is as close as possible from beta. So if you have a distance, then of course you would have beta equal alpha. But because of the entropy, what you obtain is something that is much smaller, in some sense there is a shrinking, an inward shrinking. And as epsilon goes to plus infinity, what you see is that you would converge to a single Dirac at the mean of the distribution, which is very bad. Which means that from the view of fitting, it's as if instead of matching the blue point, you map something that is very, very concentrated. So it's a disaster. So you cannot really use it for fitting problems as you would like to do for data science. So what we did with Ode is to try to find some kind of hack to fix this problem. And there is a simple hack. Actually, it's common almost everywhere. It's like a polarization formula, if you want, when you want to retrieve L2 norm, is to remove the diagonal parts. So you just subtract from your Sinkhorn value, Schrödinger value, 1/2 of the distance from alpha to itself, minus 1/2 of the cost from beta to itself. So of course, then it will fix the problem on the diagonal, but because you have minus sign, maybe it's even worse, and we'll go to minus infinity or whatever and be totally crazy. So what we did is we just tried it numerically on many examples, and it was working beautifully. It was always positive, it gives very nice fittings. So we were like kind of surprised, and I said maybe there is a theorem, and it's what we started working on during our PhD. And the first thing that I would like to insist is before stating any, I would say, new theorem, is just looking at what happened in the low temperature and the high temperature limits, because they are both like very interesting limits. The first one, as you might guess, is as epsilon goes to 0, the diagonal term vanishes and you converge to optimal transport. This is quite obvious. In finite dimension, it's simple. For arbitrary distribution, there is a lot of work. We did some paper on this to analyze how fast it converges and so on. What is also very interesting is the other limit. As epsilon goes to infinity, everyone will speak to everyone. So the optimal transport cost will just become like a big sum on n2 terms. And in fact, you can show that this converges to Euclidean distances. And this Euclidean distances is often called a kernel norm, or sometimes known as MMD, maximum mean discrepancy in statistics. So it was introduced a lot in statistics by Arthur Greton. What is it? This square norm. They are just double integral of your kernel on a measure. So how do you do this? You take alpha minus beta, this gives you a measure, and then you compute the double integral against your favorite kernels. And here the kernel you need to use to have this limit is minus your cost, so minus the distance to a power p, which might look a little bit suspicious because there is a minus sign. So you might, okay, why should it be positive? Why can it be a norm? But don't forget that you are integrating against a measure which has zero mean, because it's a subtraction of two probability distribution. So actually, and it's quite a nice result, is in some cases this guy is positive and it's actually a norm. It's called often in the literature energy distance. I don't know why they call it like this, but there is a Wikipedia page for energy distance. And the typical case is when you take the cost to be the Euclidean distance. So the theorem is if you take minus the norm to a power p, it gives you a positive kernel, so it gives you a norm if p is strictly between 0 and 2. If p equal 2, it's still positive, but it's not a norm anymore. And it's very nice. And in fact, if you look at this minus the norm to the power p, it's kind of a grid kernel of the Laplacian to some power p. So in fact, this guy in, I would say, more PD community or functional analysis is just a Sobolev norm. It's a dual of a Sobolev space, so it's a Sobolev norm of negative index, if you take the Fourier transform of this guy. So what does it tell you is that in Euclidean space, this Schrödinger cost is converging on one side to a very non-flat, non-Euclidean space, the space of Wasserstein, which is very geometrical. And the other side, it converges to a flat space, a flat Euclidean space, which is a Sobolev space. So you should view epsilon as a way to interpolate between two very different functional spaces. Of course, they have the same topologies, the weak topology of the convergence in law, but the distances are very different, and the space are, of course, like very, very different. All right. So what happened in between for other epsilon? And the theorem we proved recently is that actually it works under the condition that the associated kernel, the Gibbs kernel, is positive. So if its eigenvalues are positive, which is once again the case if D is the Euclidean distance and P is between 0 and 2. This guy is going to be a positive kernel. It's a typical example of positive kernel. So in this case, the Sinkhorn divergence, so W bar, that we have just created is positive. It's 0 if and only if alpha equal to beta. We think it doesn't satisfy the triangular inequality, and we have, I think, a counterexample for this. We need to write this down, but it's certainly not a norm, but it's something that acts like a norm. And furthermore, the topology associated to this space is the one of the convergence in law. So if W bar converges to 0, it really means that geometrically alpha is converging to beta. So at least, I mean, there's no big thing here, but it's satisfying to see that you don't lose any good property you'd like with both the Wasserstein space and the MMD space. And of course, if you do the same fitting, this non-parametric fitting, well, you remove the bias and you obtain, up to machine precision, a perfect fit, which tells you that it's something you can use to do fitting. Now the question is, what would happen in high dimension? Could you really use it in high dimension? And the bad news is, okay, it's not so clear. There's many problems. And what is the first step, the baby step, I would say, before studying any like big machine learning problems, is to look at the error you make when you discretize densities. Instead of having two arbitrary continuous densities, what you observe in practice in machine learning is just like some samples. Might be a lot of samples, but still discrete samples. So the question is, what happens when you replace the Wasserstein distance between alpha and beta by the Wasserstein distance between empirical sample? And the answer is it's very bad. And it's actually the error you make is due to discretization. It's the same as you get, if you want, when you do optimal quantization. It's something that grows exponentially with the dimension. So the error you make is 1 over n to the power 1 over d. So even if you're in dimension 5 or 6, it's going to be a disaster. So for higher dimension, if you use this estimator, of course you cannot. Okay. And really, even if the density is super smooth, like the uniform distribution, estimate, if you don't know beforehand that it's a uniform distribution, the error you would make is enormous. At the opposite side of the spectrum, if you want to estimate quadratic quantities, like quadratic norms, like this kernel norm, and everything is fine, it's just like Monte Carlo integration, you pay a price, at least in the scaling, that is independent of the dimension. The constant might depend on the dimension, so maybe in practice it's very hard, but asymptotically, you pay a distance that is 1 over square root of n, which is basically why you love like Monte Carlo method. So there is a curse of dimensionality for optimal transport. So if you want to break it, you need to change some distance to change something. And of course, as you might guess, what I've told you before is that the Sinkhorn cost is interpolating between these two guys. So I mean, intuitively, the cost of discretization should interpolate between the two, which is exactly the case. What we proved recently is that as soon as epsilon is strictly positive, as there is a bit of diffusion, then the scaling is like 1 over square root of n. But of course, there's no free lunch because the constant in front will explode with the dimension. So the constant is like epsilon to the power 1d, minus d. So the second message is if you want to take epsilon very small, then it will not be possible. So there's no free lunch. If you want to be clever and say, okay, we'll try to approximate optimal transport distance using some epsilon that is widely chosen as a function of n, then you will recover exactly the scaling of optimal transport. So it's not a method that would be able to estimate optimal transport uniformly well. I think there is no such thing. You need to have other hypotheses. But at least it's something that if you like Sinkhorn divergence, which I hope you will, you can implement it for moderate epsilon. Of course, we'd like to have more theory to understand on practical problems. If I use this, will it give me better estimator? Will it have better performance, which we don't really know. Actually, I'm not aware of much theorem in this direction. I think people in machine learning should focus more on this, especially those that do GANs, for instance. But at least it tells you that you're on the safe side in terms of scaling of discretization. So it opens the door for many more studies. So now I'd like to just sketch some possible application. And I will be clear, there is no theory. And I strongly believe that optimal transport is not the solution to this problem. It's just a nice way to frame the problem, to start the discussion. But the idea of GANs and generative model is very interesting, but also it's very problematic. There's a lot of things that we don't know and probably will never know because it's just too complicated. But just to explain the problem, maybe this would motivate some theoretical follow-up. I would like to. What is the setting? The setting is a classical setting of parameter estimation, density fitting. And I would say the starting point for this that people would do is to set up a maximum likelihood estimator. To say that my model alpha theta, they all share a common density, call it rho theta, with some reference measure, maybe, for instance, the Lebesgue measure. It doesn't really matter which one you pick, but they should all be uniformly continuous with respect to some fixed measure. And then you declare that the maximum likelihood is the one that maximizes the probability of apparition of the points, assuming that they are independent. Okay? And usually, to simplify the optimization, you take minus the log, and you minimize minus the sum of the log of the density evaluated at your point, which is kind of the same as minimizing a reverse Kullback-Leibler divergence. So you really should think about maximum likelihood trying to do density fitting using relative entropy discrepancy. Okay, so what is the problem with it? There's no problem in many situations. Like for Gaussian, it's great. But there are also many setups where the maximum likelihood just doesn't exist. It's like degenerate. So there's a lot of problems. And a typical case where it's strongly degenerate is this idea of generative model. So the idea of generative model is quite simple. Is instead of trying to describe precisely what is this rho theta or this alpha theta, you give an algorithm that draws sample. Okay? And what is this algorithm? Usually in practice, you draw a sample in low dimension. So for image processing, it's still going to be like dimension 100 or 200, I would say. And then you map this sample using a deep network in a very high dimension. Okay? So what you would observe is the composition of your initial random vector by g theta, which means the push forward of the mass from the low dimensional space to the very high dimensional space. So the geometry of the measure you want to fit is very degenerate. It's going to be like a manifold or supported on a manifold in a huge dimensional space, which means there's no way you can find a reference measure dx that would work for everyone. Because as you would move your deep nets, the surface would move, so its support will change. So you should really think of this rather as a geometric fitting problem rather than a statistical estimation problem in the sense of maximum likelihood, which would never exist. So the key aspect is, okay, you should take some discrepancy and solve a fitting problem. So of course here, since I've done my talk on this, I will sell this idea of using these Sinkhorn divergences, which is a way to generalize what people have already been doing for years, at least starting like maybe 10 years ago, of using optimal transport here or MMD, which are just two extreme cases of the class of estimator you obtain. Okay, so it's kind of a very natural way to frame the problem of density estimation in this degenerate case. So what people love nowadays, of course, is to input deep network as parameter for this model. And here, I think there's a very important take-home message is usually people use deep nets, for discrimination tasks, for supervised learning, which you should think about some method to take a very high dimensional vector and then produce some kind of a sketch or some kind of a feature map that then you can use, could be like just for classification. So maybe you have 100 classes, but really it rather act like a dimensionality reduction method in discrimination. On contrast, when you want to do generative model, you do the opposite. You start by a low dimensional latent vector, and what you want is to progressively grow its size until you reach a very high dimensional image. And I think the key idea, that I think it's a very good one, is to just use what they would call deconvolution network, which is just running the network backward, if you want. And it's really a new philosophy for image processing. And I think it's fair to say that in the last 5 years, people in deep learning, which probably comes from a different communities than image processing, they solved a lot of problems that people in image processing have been fighting for, and computer vision have been fighting for decades. So really this very simple idea solved a lot of problems that nobody knew how to solve before. This is a strong evolution, a strong shift, and it opens the door to enormous challenges that nobody knows how to solve, but at least it's very stimulating because it's opened a new area of research. Right. And it's very recent. Of course, you can do this on very simple images like the MNIST digit data sets. In this case, you can just take maybe a 2D or 3D latent spaces, and using a very simple, fully connected network, no need for fancy stuff, you can accurately model the manifold of digits using 2 dimensions. But this is not new. People knew how to do this way before. So another question is, can you generate more complicated images than just digits which are parameterized with very few parameters? And the question is, it's not so trivial because the optimization you are facing is enormous. It's an enormous challenge. For instance, think about this Sinkhorn Divergence, but you could use other discrepancies. It would be the same big issues. Is you want to compare some huge data set of points, maybe millions of images, toward a continuous model parameterized by your deep nets. And you want to minimize over your deep net parameter. So what people would do, at least in machine learning, is to throw all the algorithms they know, and the basic algorithm is some kind of stochastic optimization method, where at each iteration you replace your continuous densities by random samples. And here we are very far away from settings where you could apply classical theorem of stochastic gradient descent. So nothing applied here, so no theory tells you that this will converge, where it will converge, and so on. Just try, and in practice it gives some result, but cannot really say where it converges to. And just to insist on the computational complexity of this, what is somehow the function you want to minimize? This function is like this. It operates this way. You start from the left. You draw some random sample in dimension 100. You run your deconvolution networks. You get a bunch of images, high resolution images. Then you compute the distance with your inputs. Okay? This gives you a big cost matrix, some kind of a distance between what you have generated, the fake images, and the true images. And then you want to score out of it, so you run Sinkhorn, which you could view as another deep network in some sense, because you alternate between the Gibbs kernel, which is a linear map, and the nonlinearity, which is just 1 over x. Okay? And you iterate it a bunch of times, and this gives you the score you want to minimize to obtain the best possible GANs in some sense. So what you need is to compute the gradient of this function with respect to what? With respect to the weight in your input. So okay, don't try it at home. You could try, but it's very painful. This rather raises a fundamental question. One of the most fundamental questions in numerical analysis. I think it should be taught in any numerical analysis course, but I don't know why. With the SVD, I think it's 2 things that should be taught. At least in France, nobody taught the SVD, and very few people taught the SVD and this theorem. So I think they should insist on this. The question is, if I give you some code, some Python code to compute a function, this is just a 1-layer perceptron, probably the most simple function in machine, one of the most simple functions in machine learning, but you could imagine much more complex function. It takes capital K operation, and for simplicity, I would assume that the cost of computing the derivative is the same as the cost of computing the function, which is O of 1. So square root, its derivative would be 1 over 2 square root. It's more or less true. Now the question is, what is the complexity of computing the gradient with the function from Rn to Rn? All right. So what would be your guess? Well, what should be the complexity if you take a time capital T from Rn to R? One want to try? Everybody's trying. Say again?
I would hope for the same order that I have for the original map, but I guess there must be a price I pay.
No, you're right. It's a good answer. Congratulations. So first, what most people would do to approach this question is, okay, let's take finite differences. Maybe you could be a bit smarter, but let's take finite differences, and you need to form capital K differences, so the cost would be capital K times n. And this would be a disaster, because if n is of the order 1 million, it means no way you could compute the gradient ever. So the truth is deep learning or any complex learning task would not be solvable if this was the true complexity of computing gradient. And the answer is that the complexity of computing gradient don't depend on n. It's only depend on the time, and the answer is given by this guy who proves this theorem, is that there is an algorithm that takes exactly capital K operation. Actually, it's 2K. The complexity is 2K. And the name of this algorithm, it's actually a constructive proof. It's called reverse mode automatic differentiation. And the most important keyword is reverse. Because the way people would compute derivative in high school is forward derivative. They would compute the derivative in the same way they compose function, from left to right. And if you do this, it will be the same complexity as forming the discrete differences. And the answer is you should do this the other way around. You should transpose you should take the adjoint of the operation and form the chain rule backward. And this is capital, because if you do this, then you don't pay the price that depends on the input, you pay a price that depends on the output, which is 1. So if you have this algorithm, then backward is just you read the algorithm backward and you compute the gradient backward. So it's so simple. I don't know why nobody told me this when I was at high school, because this is the way you should compute derivative. And honestly, if you have, for this, okay, it's not so easy, it's not so hard, but if I give you even a slightly more complicated function, if you don't know this trick, no way you could compute the gradient. All right, so I think I still have a little bit of time, so I would like to just conclude. So then the idea is you would use this kind of algorithm to train your deep nets using this very complicated discrepancy value. So once again, if you have simple data set, like just images, it's fairly easy. I mean, many methods would work. And this is the input digit, and this is the output digit, which more or less look like the inputs. But it's an easy task because the data lives in a low-dimensional space. So of course, we try with more complicated images. And if you do this, then you quickly face the question of what should be the cost you have to input, the price you have to pay to compare two images. And obviously, in image processing, nobody tells you the answer. There's no easy answer to what should be the cost to compare two images. And if you use the L2 cost, it's a disaster, because everybody knows that L2 is a very bad idea if you want to visually have a good comparison of images. So the other revolution in these generative models come from this guy and his co-author, Ian Goodfellow, who introduced the idea of GANs, which tell you should look for a cost in an adversarial way. You should introduce a second deep net, which would be a discriminative deep net, and you try to maximize over this deep net to make the method the most discriminative possible. So then the problem becomes the min-max, because you want to minimize over your generative network, and you maximize over your discriminative networks, which opens the Pondera box of min-max optimization, which is very complicated. So it's like everything that I've said before, but even worse. Nobody knows any probably converging algorithm that would give meaningful results. Just in practice, any reasonable algorithm works with a lot of hack to make it stable. So it opens the door to many questions for this. We've used it on small laptops. What you can do is small simulation on very small images. You create images that looks like the inputs. So these are images of celebrity, like 64 times 64 images. And you can generate images. If you look closer, actually, you can see there are some artifacts. You can clearly see from the visual eye that they are not really realistic. But the idea is just take your network, just double, quadruple the size, just multiply the number of data by 10, 100, and then you get very impressive results. So these are the results people at NVIDIA got last year. But this year, there are even new submissions that gives even more incredible results. And what people would do to assess the quality, because it's so high dimension, nobody can do statistics in so high dimensional space, is to look for interpolation. Because they want to use it like for special effects, for movies production, for video games, and for many applications like this. So they really care about having smooth transition. And it's incredible. So if you do this, you just take 2 points in the latent space, then you draw a straight line in latent space, and then you lift this straight line to a curvy line on the space of images. And this is a video you can find on YouTube, which is a very high quality video in terms of resolution. You can still see a lot of defects, but believe me, in a few months maybe, you would see no difference with the input. And these are virtual celebrity in some sense that is not in the input. And you can see the transition, which gives you this kind of very complex deformation, very nonlinear deformation, that it's impossible. I mean, no way you could get this before without using these two networks. There's no way you can encode the apparition of hair and stuff. So it's really, really impressive. But once again, this is just visual effects. And it's probably a very poor statistical estimator because probably this doesn't respect at all the statistics of the input, but it gives you beautiful images. So the question is, if you care about statistics, you are in some settings where you should not be biased, you should represent the data in a faithful way, in a fair way, then probably this is not the way to go, but okay, how can you do? In so high dimensional space, no way you can compute even the Wasserstein distance or whatever. So it really opens the question of how you would assess the quality. Okay, it's really like open problem. So just to conclude, so I would say the history of optimal transport is really like on PDEs and functional analysis, probabilities, so very theoretical, a lot of very strong results, including 2 field medals. So Figali got the field medal last summer for his contribution to the regularity of the optimal transport map, which is very technical. But I think now the question, and very complicated, and now the question is how this insight in geometry of the optimal transport could impact problems where there is a need for geometry. So, I mean, some of the key ideas, if you are in high dimension, you need to do something to regularize. So entropy is the simplest way to go, but there's probably other ideas. If you are in high dimension, how do you assess the quality? What should be the score function you want to use? It's not so clear, and nobody agrees. So we should think about what should be the performance quality measure. It's also connected, I think, to the question of metric learning. How do you learn a metric in high dimensional space? I think the idea of doing a min-max is promising and works in practice, but there's no theory on this. Like statistical estimator using min-max, apparently nobody knows, but it seems very interesting, even for statisticians. And the last thing that maybe we'll discuss this afternoon in the Blackboard session is what happens if the data don't live in the same space. Like if you have 2 shapes that live in two separate space, maybe you want to compare graphs, for instance, which are not really in Euclidean space. And there is a nice idea to do this, is the idea of Gromov, of instead of looking for an optimal transport, you look for rather a quadratic assignment. So it's kind of an extension of optimal transport. And it's nice from a theoretical perspective. It also defines the distance. But from a computational perspective, everything is NP-hard, so it opens the door to many challenging problems. And I will stop here, and thanks for your attention.